This is the video for uniform circular motion. For those of you following along in the textbook, it's pages 63 to 65, 114, and 371. The first thing we will cover is section 3.9, which is just the basics of uniform circular motion. So in uniform circular motion, what you have is an object, like that, moving around in a uniform circle. It travels at a constant velocity, c v1 equals v2, and the velocity is always tangent to the circle. However, there is acceleration, and the acceleration is always inward into the circle. And the value of that acceleration is equal to velocity squared over r. From this, then, we establish that as velocity increases, the acceleration will increase, and as the radius increases, the acceleration will decrease. Another way we can look at this uniform circular motion is from the time period. For example, during a period t, which is 1 over f, we can determine the velocity by plugging into this equation here, where the velocity of the object going in a uniform circular motion will be equal to 2 pi r, which is the distance, over t, which is then the period. So another way to look at it is 2 pi r times the frequency will be able to give you the velocity.
So as we covered before, the velocity is equal, like the acceleration is equal to the velocity squared over r. Also, we know that F, force, is equal to mass times acceleration. So the force acting inwards upon the mass that's going in uniform circular motion is always going to be, it's going to be mt squared over r. Alright, so here are the equations we got from before. So now that we have the ball or the object going in uniform circular motion, what would happen if the force acting upon it disappeared? Would it either continue going in the direction of the circle? Would it go straight away tangent to the circle? Or would it go away from the circle? And the answer is surprisingly simple. Because the only force acting upon the ball is going inwards, the centripetal force, once that disappears, there will be no force acting upon the ball, well, except for air friction and stuff like that. So that means that it'll just continue in the direction it was going, the v that was tangent to the circle. So the direction something will go once the force stops acting upon it is always going to be tangent to the circle.
So as Lucas said, the only force is going inwards, and we know from Newton's second law that an object will continue in its path unless an outside force is directly acting on it. And that's why the ball or whatever object it is will always travel tangent to the circular motion it's moving in if the centripetal force stops. And this like misconception comes from the differing like experiences between centripetal force and centrifugal force, which because we've all experienced like driving around in a car and seeing things fly off to the side. That's due to inertia, which is due to like Newton's first law of motion. There isn't actually a force acting on it, but it wants to continue in its movement, and that's why it moves out of the way, and that's why some people pick C.
Alright, so this here is an example of uniform circular motion. What we have is the mass here traveling around in a circle, and you can see that it's not leaving the circle, just staying in the circle. The only force acting upon it is the force from my finger pulling it inwards so that it goes constantly in the circle. But something cool about this can also be an example of simple harmonic motion. Alright, so what we have here is a uniform circular motion. But, as I said before, we can actually do simple harmonics with this. Now, when you see it, it looks like it's oscillating, even though it's not really, because you're looking at it from a plane where you can't see it moving rotationally you only see it moving in the x direction, it looks like it's oscillating in the x direction, you can actually derive the equation for that.
So this is the derivation of how uniform circular motion is also simple harmonic motion. In this part, we see the top view of a circle with radius a, and the object is moving around the circle in uniform circular motion with tangential velocity v sub m. We see that the angle it travels through is theta, and the original angle is phi. We know that the x coordinate of whatever point it's at that point is x, and using that we can solve for the y value, which is the square root of a squared minus x squared. We know that how the horizontal velocity and the tangential velocity are related, and using that we do v over v sub m is equal to the square root of a squared minus x squared over a. And because simple harmonic motion is only viewed from the horizontal direction, we solve for the horizontal v in terms of the other variables and get v is equal to v sub m times the square root of 1 minus x squared over a squared. So this is the side view, and because we know that it's only in the x direction when viewed, is uniform circular motion seen as simple harmonic motion. We can apply the simple harmonic motion equation to this side view. And we know x is equal to a cosine of theta plus phi, or theta is equal to omega t, where omega is the radial velocity of the object moving in uniform circular motion. And to check to see if this corresponds with our original view of uniform circular motion, we solved for the period, and we get omega is equal to v sub m over a, and we know that v sub m is equal to 2 pi times a over t. So we solve for omega, which is equal to v sub m over a, which is equal to 2 pi times a over t over a, which you get 2 pi over t, where t is the time it takes to complete a full revolution. So you get omega is equal to 2 pi times the final frequency, which confirms our original not top-down view of the circular motion, in which omega is equal to 2 pi times the frequency also. Yeah.
All right. And
So we're going to start with a very simple uniform circular motion problem. For this problem, we are given that a 900 kilogram car is moving at 10 meters per second in a circle that's 25 meters in diameter. So let's just write down the given first. We know that m is equal to 900 kilograms. We know v is equal to 10.0 meters per second, and that r is equal to 25 meters. And the problem asks for us to solve for a and f, which is acceleration and the force acting upon it inwards due to the centripetal friction force. So in order to do this, we got to apply our uniform circular motion equation. A is equal to v squared over r. Now we just plug in values. To get 4 meters per second squared. Now we can combine that with Newton's second law, F is equal to ma, to get F is equal to mv squared over r. And then we plug in values again. To get 3,600 newtons for the force.
Now let's move on to something a little more complicated. In this problem, we have a spinning pendulum that rotates around in a circle and is attached to a string. It moves around in a circle with a radius r, makes an angle with the vertical theta, and has a mass of m and is attached to the ceiling with a string of length L. So first thing to do in this problem is to draw a force diagram. In this we have the mass, we have the angle force of the string on it, Ft, for tension, and force of gravity. Now we can split these up into force of this tension force in x and y direction. So we have Fy and Fx, and that can be obsolete. We know that Fxy or Fty is equal to Fg because the mass is not falling. So we can set up an equation based on that, where Fty is equal to Ft cosine theta, which is equal to Fg, which is equal to mg. So together we have the equation Ft cosine theta is equal to mg. And from our circular motion, we know that Ftx is equal to ma, which is equal to mv squared over r. And we know that f sub tx is equal to f sub t sine theta. So we get f sub t sine theta is equal to mv squared over r. And now the problem asks to calculate in what direction is the acceleration of the ball and what causes this acceleration. Qualitatively, we know that the acceleration is inwards based on centripetal force. But the second part is to calculate the speed and period of the ball in terms of L, theta, G, and M. Now, based on the equations we have, we can solve for V to get, which is the speed, to get V is equal to the square root of R F sub t sine theta over M, which is equal to the square root, pardon the bad handwriting, of R over M times mg over cosine theta sine theta, which then in turn is equal to the square root of Lg sine theta squared over cosine theta. And that would be the speed of the mass. The period is simply 2 pi L sine theta over V. So you get T to 2 pi L sine theta over V. And plugging in V for Lg sine squared theta cosine over cosine theta for V, you would simplify to get 2 pi times the square root of L cosine theta over G.
How do I stop this?